Welcome to How to Invent the Internet. My name is George Verghese, and I'm a professor in the Computer Science Department at UCLA. This video is based on interviews with 5 Internet pioneers, Len Kleinrock, Bob Metcalfe, Radia Perlman, Paul Mockapetris, and Vint Cerf. These interviews happened in the fall of 2020 during my networking class CS 118 at UCLA. COVID-19, large online networking class at UCLA, how to deal with issues like online cheating, rats. I was complaining in my head when I listened to a message in my Indian church which said, stop complaining, but see COVID as an opportunity. And then it struck me that Zoom, while it lacks physical presence, makes it possible to interview any expert anywhere in the world in class without the expense and hassle of travel to Los Angeles. Since my class is more about discovery than about details, I thought it might be a good idea to invite 5 of the creators of the internet as we know it. And I happen to know 2 of them quite well, 2 of them slightly, and 1 of them I didn't even know at all. But when I emailed them, they all agreed. And so I felt this was a sign to continue. The format of this whole interview series was a set of 40-minute interviews in class by students. And while I'll try and post the longer interviews later, I thought it's a good appetizer to have a few 5-minute snippets, and we'll try and present the longer version later. And at the end of these interview snippets, I will try and talk about some of the things I learned in terms of patterns of discovery to discover the internet or anything else.
You mentioned Claude Shannon, and I'm glad you're going to be teaching about him today, because one of the things I was going to say is, if you haven't heard of Claude Shannon, spend tonight reading about him. The man was remarkable, and he has lessons for research and his whole approach. And one of the things that he taught me when I was a student is that you want to study systems when they get large, because when they get large in terms of numbers or throughput or nodes, then properties emerge that you won't see with a 5, 10, 20 node, 50 node system. So if you scale large, things will happen. And very often what happens is the stochastics go away and becomes far more deterministic. You know, that's called the law of large numbers. And that has a very enormous impact in the way many systems behave. In fact, the title of my thesis proposal was Information Flow in Large Communication Nets. I specifically wanted it because if I studied a 2 or 3 or 5 node network, what would I learn? You know, there might be some principles, but nothing fundamental. So scaling was an advantage, a challenge, and I knew it would be more meaningful if I could study systems in the large and watch their emergent properties. And in fact, that's what I did. So the scaling, it wasn't to see that this system would become successful and spread across the world. From my point of view, it's more a scientific study and curiosity. What's going to happen if we enlarge them?
Got it. So Len, how about for the students, right? Can you sort of, does that still apply to them as they go on into their careers?
Oh yes. In terms of advice to students, I've got so much it would take an hour. But part of my advice is I'd like to conduct what I call the 100-year test. And this concept came from me from another great researcher in the past, Dick Hamming, famous Hamming code, Hamming matrix, etc. He asked a question. He wrote a great paper one time. He said, why is it that so few scientists are remembered for their work? And his answer was, they don't work on important problems. And so he asked the question, will your work be remembered 1,000 years from now? Now ask yourself, what do you remember that happened 1,000 years ago? Of course, you remember very little from 1,000. So how about 100 years? The 100-year test. Will your work, what you're working on right now, we're going to do in the next few years, be remembered? How about 10 years? The point is, it won't be remembered unless you work on something important. So think of that. think of all the work that you're doing as being important, address it that way, and present it in a way which will have longevity. You shouldn't waste your time fooling around with something that won't even give you gratification. So that's one thing. Second thing, this is a radical statement now. I think that computers are the worst enemy of critical thinking. And the reason is that guys and gals like you just depend too much on simulation to evaluate a system. And I remember I had a student one time came by, I gave him a problem. He set up a model, he couldn't solve it. He came by and he showed me the simulation results. Says, this is the answer, this is how it behaves. I said, oh, why does that line look like it has a straight line portion? What's the meaning of the slope?
So this is Tomer, and
Hi.
did I get the pronunciation right?
Oh, yeah, it's all good. Yeah, my name's like very often auto-corrected. But yeah, thank you. So my name's Tomer Laufer. I'm a computer science undergraduate, and I think you touched on my question with the world of like an office full of personal computers at every level. But my question was, what were the problems with the rat's nest at the mainframe that prompted you to invent Ethernet? Did you mean the cables from terminals that all met at the home plate at the mainframe? And what kind of cables were these, and like how thick were they? Like what kind of problems did they create?
So in my first presentations of Ethernet in the early days, still back at Xerox PARC, to my colleagues, was a picture of a rat's nest. And it was positioned as one of the problems we wanted to solve. We wanted to not have a rat's nest. It was hard to manage. Dave Boggs and I were constantly in the closet. The connectors would break, the cables would pop out of the connectors and so on. These were RS-232 connectors. The cable was, I don't know, the cable was about three-eighths of an inch thick, had multiple connectors and multiple wires in the cable. And the connectors were I think it was called the DB, well, there was a DB9, a DB15, and a DB25. That's the number of conductors in each of them. So we judged them to be expensive and unreliable. And plus we were in a research center. And in our research center, one of the themes promoted by the biggies, like Alan Kay and Butler Lamson and Chuck Thacker, those biggies, they were all promoting a thing called distributed computing. So we decided in the network space, we were going to try the most distributed network you could think of. So the network that Charles Simoni had been working on before he went off to do the text editor, which became Microsoft Word, he was working on recreating the ARPANET inside the building with little packet switches. And as soon as I got involved, I threw all that out and went to try to get the most distributed network I could think of, because that was our theme. So it turned out that that would mean as few wires as possible. What's the smallest number of wires you can have in a network? 0. And so we looked at the radio networks, and the Aloha network was a packet radio network. The trouble is the modems in those days were as big as the PC we were building. They were about this big. So we couldn't use radio. So we couldn't use 0 wires. Well, what's the next biggest number? 1. So we decided to have 1 wire, which turned out to be a 1/2 inch thick coaxial cable that went 1 kilometer. And then the stations would tap into it. And we viewed this as an improvement over the rat's nest. The rat's nest was all these wires, and you had to home run. Every office had to home run to this wiring closet. So we had this shared cable that went down the center of the corridor, and then each office would tap into the cable as it passed. And we viewed this as an improvement on an even more distributed network. We went further. We wanted the algorithm for managing the sharing of this cable. So all the stations, all of these Alto PCs could inject and receive packets from the cable, but how would they take turns? How would they keep from stepping on each other or colliding, as the term emerged? And that's what caused me to spend a month, it was tough duty, a month in Hawaii studying the Aloha network. And we adopted the the sharing algorithm of the Aloha network, which was randomized retransmission. You send, if you don't get through, you randomize and try again later. And the purpose of the randomization is so that the collisions will not recur over time. So we did eliminate the rat's nest for the first 10 or 20 years of Ethernet, but guess what? The rat's nest is back.
Right.
So now the shared cable is gone, and the economics have all changed. Memory is now cheaper. The speeds are a lot faster. So now it's not a shared medium anymore on cable. It is still shared in Wi-Fi. So there is a channel conflict problem and randomized retransmissions and so on occurring in Wi-Fi, but not in Ethernet cabling. By the way, the terminology I use are wired and wireless Ethernet. And wireless Ethernet is called Wi-Fi.
They said, our customers would never want to do that. So years later, when these people had made lots of money for the company, because their stuff was good, it would have been just as good had they done it properly, which was on top of layer 3. Yeah, so they were all heroes. And then our manager, who, as I said, was the smartest person, one of the smartest people I've ever worked with, he said, Radia, we need to design a magic box that will sit between two Ethernets and let somebody on one talk to somebody on the other. And, he actually asked me to do the spanning tree algorithm. They already had the concept of just moving the packets around, but without a hop count and stuff, you needed to have a loop-free subset. So, the constraints were not changing the end node in any way, not having any spare fields in the Ethernet header and having a hard size limit. And then he thought it was going to be really hard. He said, with no configuration whatsoever, it just breaks all the symmetries and does this. And then he said, and furthermore, just to make it a little more challenging, and he thought he was being funny, I think, he said, make it scale as a constant. So no matter how many links and bridges there are, the amount of memory necessary to run this should be a constant, which is absurd. Nothing's a constant, linear is the best. And then he went away for a week. And this was before cell phones or people reading email. And that night I realized, oh, it's trivial. I know just how to do it. And it scales as a constant because to run the spanning tree algorithm, you just need to remember the best message on each port. A message is about 50 bytes. So if you have 7 ports, it takes 350 bytes to run it, no matter how big the network is. So yeah, that came from that as well. So usually either somebody asks me a problem or I notice something that is annoying me, usually around usability, making things like self-configuring or whatever.
Got it. So we have one more person, who's Alyssa, and then I'd like you to read your algorithm, and then we can move on to your presentation. So Alyssa, can we get, yes. Hey, there you go. Hi, Alyssa. Yeah.
Hi. Okay. Hi, Radia. So nice to meet you. Thanks for being here. So kind of just off of that question, my question is, what were some of the biggest roadblocks, either technical or non-technical, that you encountered while developing the spanning tree protocol, and how did you overcome them?
Well, the spanning tree was in 1 week. I knew exactly how to do it the first night. I spent Monday and Tuesday writing the spec, and I got it in enough detail that when they started implementing it, it just took them a month or two without asking me a single question. So, and that was like Tuesday. And then my manager wasn't going to be around for until the next week, and I couldn't concentrate on anything else. So I spent more time on the poem than I did on inventing the algorithm and writing the spec. So I guess the biggest roadblock was trying to find the original trees poem, because this was before the internet. So I knew the first and last stanza, everybody knows those. But I wanted to know like how many stanzas it was. And so I went to the librarian at Digital, and she didn't really know or where to find it or anything. But then I eventually figured out how to find it, which was my mother has this amazing memory.
I mean, I think he's talked a lot about his design and why he thought it was a good problem. I guess my question was more, why did you design it the way you did versus a simple database to replace host.txt? But you talked about it a little bit, but did you know that like what you were doing was going to be extensible? Like, did you know the problem you were working on was going to be something big?
I think what I had in mind was the idea that the whole population of the US should be able to have their own domain names, just abstractly.
Wow.
You know, there was no obvious limit to the size. Again, I think, you know, that a database could have solved the problem, but it wouldn't have solved the distribution problem. The databases of the time, I don't think, were up for being able to, you know, solve the distribution problem, because you know, I've done consulting for a bunch of companies about how they should implement DNS, and usually I tell them you should be self-sufficient. And what I mean by that is your internal operations should work regardless of whether ICANN gets compromised. You know, there's all of these things about how you know, China doesn't like the fact that there's a US organization that runs the root. You know, there's all these arguments about who owns the root. And, you know, whether it was Shell Oil or Boeing, two companies that I consulted with way back when, I said, you know, you want your internal DNS to work regardless of what happens on the outside. You know, I don't care. You know, assume the worst case where terrorists have, you know, reprogrammed the root. You know, you want your network to work. One of the things, over time, one of the things that happened was the state of California was, you know, runs under ca.gov. And once upon a time, the people that ran .gov discovered that there were 2 computers in the state of California that were infected with pornography. So they turned off the delegation. Okay, so, you know, the California legislature and the highway patrol couldn't talk with other sites for a while until the ca.gov thing was restored. And, you know, I talked to those people and I said, well, you know, you can blame the people running .gov for this if you want, but in reality, you should blame yourselves. You know, you should be able to run internally regardless of what happens. And, you know, I still believe that, you know, to some extent, when you take a look at the original design of DNS, one of the requirements was you should be able to retrieve data from anywhere. So if I want to send, you know, email to the Philippines, I don't have to, you know, I should be able to find Filipino email addresses and servers, regardless of, I don't know anything about the structure of the Philippines top level domain. And so one of the design things that happened was we said, well, okay, if you can find your way to the root and you can always descend one level in the hierarchy, you can eventually get anywhere. So that's one of the design principles of the DNS in particular. And I had always assumed that people would come along and upgrade that. And what I mean by that is there's, you know, what you could have done is you could have said, well, okay, we're going to have uplinks. And then I can navigate up to find the root from where I am, even without the bootstrapping information that's, you know, commonly put into a server. You know, I always thought that, oh, down the road, what we'll do is we'll fix that so that you can, if you're, you know, UCLA, you know, .edu, well, you know, UCLA knows that it's the child of EDU, so it should be able to talk to EDU, and the EDU is a child of the root, and so you should be able to find that. And in reality, if you think about a tree structure, you can probably grab any node of the tree structure and kind of shake it and think of it as your root if you want to. So I always thought that people would come along with, a more sophisticated way to, avoid having to have bootstrapping information about the root. But that was one of the pieces of work that never got done. But there's no reason why we couldn't do it.
So much for being here. My question to you is, for all the other great internet pioneers, Radia, Len, and Bob, they all agreed their innovations flowed from great problems they were assigned to. For example, Paul Mockapetris, it was being assigned to find a naming service to replace host.txt. How important would you say your collaboration was with Bob Kahn in finding that great problem?
Well, in fact, Bob was the one that posed the problem. We worked together along with a bunch of other people on the ARPANET, and Bob's role was on the packet switch side, the so-called interface message processors, and my role was with Steve Crocker on the host level work on the ARPANET. So it's the host-to-host protocols, NCP, and the subsequent applications like Telnet and FTP, eventually email and things like that. When Bob Kahn showed up in my office in the spring of '73, he arrived saying that we had a problem. And my reaction was, what do you mean we? And he explained that the success of the ARPANET propelled further interest in the Defense Department in the use of computers for command and control. And the immediate implication of this is that the computers would end up in ships at sea, mobile vehicles, and airplanes. And the ARPANET development, very successful development, was based on dedicated telephone circuits connecting the IMPs together and then the host connected to the IMPs. And you can't use wires to connect the tanks because they run over the wires and they break and the airplanes don't make it off the tarmac and the ships get all tangled up. So Bob had already started working on a packet satellite program for the long distance ship to ship and ship to shore, and also mobile packet radio, which was pretty ambitious for the time. First of all, it was involving CDMA, which, remember, this is the early 1970s. We were using, great gigantic surface acoustic wave devices for counter-propagating, codes. And the radios were about a cubic foot and cost $50,000 each, but they were running at 104 to 400 kilobits a second, operating up in the 1710 to 1850 band. So his proposal was that we had 3 different packet switch nets with different size packets, different latency, different error rates, and different data rates. And somehow we had to figure out how to get them all to look uniform. And oh, by the way, we weren't allowed to change any of the networks. And they didn't know that they were part of the internet. Each network thought it was the only network in the world. So that was the problem. We called it the internet problem. And it didn't take very long for the constraints on the problem to dictate what the solution had to be. We had to put computers between the networks that knew that they were part of the internet, because the networks didn't know that. The host computers needed to know they were part of the internet because they had to refer to hosts in other networks than the one that they were connected to. So you can almost see some of the solution just percolating out. We had learned about layered architectures from the ARPANET experience, and we adopted that engineering posture for the internet design. And we made some other really important choices. For example, we decided that the internet layer of protocol, which was embedded in the original TCP and then split out distinctly after the 3rd iteration of TCP/IP design, we knew that we did not want the internet protocol to know anything about the underlying transport system. We didn't want it to know anything about what specific communications technology was being used to carry the packets. And the reason we wanted that isolation is that we knew there would be new communication protocols.
Let me end by speculating on some common features or patterns that can be seen in the different stories of these inventors, even though they're all so different. So I'm inspired by a mathematician called Polya, who stimulated me as a young boy with a famous book of his called Patterns of Plausible Inference. And I'd like to see whether we can learn from these interviews to shift from inference to invention. So Polya's book really was targeted at math students who disliked the fact that math books stated results and proofs and not how a student could invent them. Similarly, you could argue that networking books describe protocols like Radia's spanning tree or Paul Mockapetris's DNS or Bob Metcalfe's Ethernet without actually giving them any idea how they could have invented them. So during the course of this interview, we did see some common patterns or features. Each pioneer was given a great problem by someone. Each had a unique background or DNA, which actually led them to approach the problem differently. Each of them then introduced a novel solution approach. Further, each had this belief that made them want to design a scalable solution that would scale beyond the immediate need for the problem. And then, though, they didn't just stop there. They found effective vehicles for propagation of their idea to the world, and they were committed in the long term to continuing the long-term flourishing of their idea. Here is the table with some more specific examples of each pattern for each inventor. I will only go through the first and second columns because it would take too long. And so again, the rows are problem, the person, the solution idea, the unique DNA, the scalability notion, the propagation vector, and how they continued the idea. Okay, so Len Kleinrock heard about his advisor, Ed Arthurs, talking that someday computers were going to talk to other computers, and there was even some government projects that no one had seen. So Len began to wonder whether breaking up the data between the two computers into messages or so-called packets that traveled independently of each other through the internet would have a better use of resources than the current paradigm, which was the telephony idea of reserving a resource for a phone call or a communication duration. Now, Len's background in information theory and the influence of Shannon, hopefully you remember this snippet, led him to a mathematical investigation of the benefits of packet switching, especially for a large number of computers talking to each other, which is quite foresighted because in those days there was only maybe two or a few computers when he started. He was then able to propagate the idea by conversations with DARPA and his friend Larry Roberts, and that convinced him to sign on to have UCLA write the first software for ARPANET routers. Finally, he remained committed to the success of packet switching for the long run, and especially working many years later on the Gore report, which helped usher in high-speed networks and NSFNet via government funding. For the second column, we look at Vint. His problem was he actually, a little background, he helped write the software for the first routers even while he was a graduate student at UCLA. So he worked at with Len. And then he went to work as a professor at Stanford. His colleague, Bob Kahn, as he says in the snippet, actually gave him the problem of interconnecting two different government networks, the ARPANET, which was full of landlines, and the packet radio network, which is full of wireless links, which had very different properties. And they didn't actually talk to each other or couldn't talk across each other. And this led them both to invent what is now known as TCP/IP, and later to separate TCP from IP, which had been conjoined in the ARPANET. Vint has always been active in propagating TCP/IP in forums like the IETF and Interop, and has always been invested in the continuing success of the internet by helping propagate the privatized internet via organizations which he founded like ISOC and ICANN, which you can read about if you don't know. So what does this teach you about discovery? What does it teach you if you're a student who is very young and wants to do something for yourself? Perhaps it should encourage you to find a great problem that matters. Second, to be yourself and use your unique background. whether you're watching this video from Afghanistan or whether you are a young girl somewhere in Sri Lanka, right, or in India, and to be yourself and to use your unique background. And then look for a simple and scalable solution, a solution that scales beyond the immediate problem. But then don't stop there, right? You will need to find and work on some kind of vehicle to propagate the idea and ideally be committed to the long-term flourishing of your idea. I hope after seeing some of these snippets, if you're a young person, you see that these are people like you. And just like them, you can invent things for yourself. I hope you also see them as real people. Okay, Len mentions his granddaughter and Radia mentions her mother. And I hope you are as moved as I was by Vint's answer to Keanu.
Hi. So some students in this class have a disability and are part of the CAE program at UCLA. Last night I read that you have a hearing disability for many years, as did your wife. So I was wondering if you could give any words of encouragement to these students based off your experience.
So, well, first of all, don't give up and don't take no for an answer. And I think help people to be comfortable helping people know what it is that will make it easier for you. You should not be afraid to ask people to be helpful. And some people don't know what to do. They're afraid to ask. They don't want to embarrass anybody. And I think you need to take the initiative to say, I need to see you face to face, or I won't hear you, or I can't see a thing. So, you need to pay attention to that. And if someone's, here's a good example. If you're blind, for instance, the thing you don't want is somebody grabbing your arm. What you want is to be able to hold your hand on the elbow of the other person, for example, or put it on their shoulder. And so you can track what's going on, but you don't want to be dragged around. And I learned that by asking. And so the big deal here is for people who want to be helpful, they should ask, how can I be helpful? And if you need help, you shouldn't be afraid to say, and this is how you can help me.
So finally, a thank you to all the pioneers, Len, Bob, Radia, Vint, and Paul, for agreeing to be interviewed and answering so many questions of mine. And a big thank you to my wonderful UCLA undergraduates, some of whom were courageous enough to volunteer to ask these famous people questions, not for the faint of heart. And there are too many of them to thank because many of them were in part of the long interviews, but the 5 of these have been featured in this. There's Tomer, there's Elisa, there's Danielle, there's Isha, and Kiana. Thank you to all of them, and thank you to all of you for watching.